Lesson 4.7 is going to be the scale change images of trigonometric functions. And so if you're gathering up the things you're going to need for this lesson, you're going to need one blank note card, and you will need your graph and calculator, and you'll need the video notes for 4.7, and that should be about everything you're going to need, I think, for this lesson. So if you need to stop and pause the video and gather those things up, go ahead. The big idea of this lesson is that of using the graph scale change theorem, which you know to be the one f x comma y equals ax comma by that we learned back in chapter 3. And we're going to use that to see how we can apply this to trigonometric equations and the amplitude and the period of them and what happens when we have a scale change. So we'll need to read lesson 4.7 in the book, but it starts out talking to you about sound waves. And sound waves, or pure tones as they're called, are tones that are produced by a tuning fork as it travels in a sine wave, meaning that it's just going to be a wave that goes like this. It's going to repeat itself over and over and over again and so on. Okay? And this pure tone, or this sound wave, is considered a sine wave. Now when we talk about sine waves, that's different than talking about a sine function or a cosine function. The sine wave, and they're all called sine waves, could be the image of a graph of either a sine or a cosine function. Alright? So we won't worry too much about the tangent function for this because we're not going to have graphs that have vertical asymptotes in them. But we're just talking about sound waves that over and over and over again repeat themselves. Okay? There's not even really an axis for them. They're just out there repeating themselves in space. Alright? And so the two terms that we need to talk about when we talk about these sine waves is the idea of amplitude and period. Now amplitude is the distance from the highest point to the lowest point. So you can see they drew that straight down here perpendicularly. The distance from the highest point to the lowest point, not along the curve, but straight down altitude distance, and then it's half that amount. So if you wanted to think of a line like this one cutting halfway through the figure, then the distance that you would rise above that line and fall below that line, that would be the amplitude amount. Or you can take the total distance and divide by 2. Okay? So they say it's 1/2 of the segment DE right here, the length of segment DE. Now for the period, we're going to measure how long it takes in linear distance along our x-axis to repeat one whole time of the curve. So if we started at point D and we went through one whole period, we'd wind up at this maximum point right here. So the distance from max to max, let me change pen color here. I could take the distance from this minimum over here to this minimum, okay? That distance. Another thing I could do is I could say, well, I'm going to go from this 0, which is on the increasing part of the function, and I would go all the way over to this 0 on this increasing part of the function. So this distance right here. So these three distances, if I measure them, are all the same, okay? And that gives us the period of the function. Alright, when we talk about the sine waves, the pitch of the tone is related to the period of the wave. The longer the period, the lower the pitch, and the shorter the period, the higher the pitch. So if I extend this, pen work here. If I extend this way out, like so, and make a really long period out of it. So from max to min back to max here, this distance is a really long period, then I'm going to get a lower tone. Okay? If I make it cycle really short, so the distance from max to max or min to min like this is really short, then I'm going to get a higher pitch. Okay? a higher pitch. The intensity of the tone, so the loudness of it, is related to the amplitude of the wave. Okay, the amplitude of a sine wave is half the distance between the maximum and minimum values. So if this just goes up the normal amount and down the normal amount, then that would be considered, maybe the parent function. If I had a very short distance between the max and the min like this, then it would be really, really, really soft. If I make it go up and down and up and down and up and down and up and down like this, and I increase the distance between the max and the min, then that's going to make it really loud, okay? And then, of course, I could go loud and low, loud and high, high and soft, and high and not very loud, okay, or very loud. All right? The formulas we're going to add to our note card are going to look like this. You may want to pause and get the note card and write this down, but I'll try to explain it to you a little bit. Functions that are defined by y equals b times the sine of x over a, or y equals b times the cosine of x over a, because remember, a sine wave could be a sine function or a cosine function. They're going to be having the scale change applied to them. So this scale change from before, s, x comma y equals ax comma by. The amplitude will be the absolute value of b. The amplitude will be the absolute value of b. So if we know this rule, the absolute value of that number right there will be our amplitude. If we have a formula, this word coefficient or cosine, or the word sine right here, the coefficient of that will be b. That's because they took this, y over b equals the sine of x over a, and they multiplied both sides by b, and they parked it in front right here. It'd be the same thing if this said cosine. The period will be defined as 2 pi times the absolute value of a. So we need to know the a value from that rule, from that scale change rule, and the absolute value of it times 2 pi will give us the period of the function. Now, frequency is the reciprocal of the period. So if 2 pi times the absolute value of a is period, and that's all over 1, when I reciprocate it, I get 1 over 2 pi times the absolute value of a, 1 over the period. It represents the number of cycles the curve completes per unit of the independent variable. So if we make it cycle faster, then the pitch will get, remember what we said up here? Make it cycle faster, the pitch of it will become shorter, okay, and higher. We can make it cycle more slowly, make it become lower, a low note, okay? When a sine wave represents sound, doubling the frequency results in a pitch 1 octave higher. And make sure you make a note about that, because we are going to do some functions where they'll tell you to take it up an octave or take it down an octave. But that just means when you double the frequency, the pitch will be 1 octave higher. Doubling the frequency makes the pitch 1 octave higher. Okay, that said, I think we are ready to try the video notes, and we'll see if we can dissect and look at some of these equations. And if we can, we should be able to then also tell what's happening to the sound waves as we go through it. All right, so I'm going to switch over to a different worksheet right here. Okay, so for the first example on the video notes, it wants us to graph y equals 4 times the sine of x. For negative 2 pi is less than or equal to x is less than or equal to 2 pi. So we could have, let me get my pen to work here. We could have actually written this as the interval from negative 2 pi to 2 pi if we wrote it in interval notation. So you'll kind of see a variety of notations here, but that's what that means. Okay, so what we want to do is we want to determine all of these things, analyze it, and find out what the period, the amplitude, and the frequency are, and then we're going to graph it, and we're going to say how it is related to the graph of y equals sine x, which this would be the parent function here. Okay? how it's related to its parent function, which we learned how to graph in lesson 4.6, didn't we? Okay, so to do that, we're going to look at this as y equals 4 sine, and then I'm going to write this as x over 1. So it's going to be the mirror image of what's on your note card, which says y equals b times the sine of x over a, right? So if we were going to write out the scale change rule for this, it'd be s, x comma y, equals ax, so that would be 1x, comma, by, so that would be 4y, wouldn't it? Okay? That would be 4y. So here's our scale change rule right here, where a is 1 and b is 4. A is 1 and b is 4. Okay, so when it asks what the period is, we're going to use your note card if you need it. The formula for period is 2 pi times the absolute value of a, isn't it? So in our case, that would be 2 pi times the absolute value of 1, that would be 1, which is just going to give us 2 pi. So it's going to have the same period as the parent function, isn't it? When it asks what the amplitude is, that's the absolute value of b. The absolute value of b would be the absolute value of 4 in this case, which would just be 4. That means it's going to go up to 4 and down to negative 4. So the highest it will be 4, and the lowest will be at negative 4. When it asks for the frequency, remember the frequency is 1 over the period. So that would be 1 over 2 pi, which means it cycles once every 2 pi. Cycles once every 2 pi. Okay, so let's graph it, and let's see what's happening with it. All right, now it's a sine function, and so we know the sine function is going to start right here at 0, 0, isn't it? Okay, that's because if you go back to your unit circle, this is 0, this is pi over 2, this is pi, this is 3/2 pi, and then back to 2 pi right here. If I were looking at the sine of 0, that's the ordered pair 1 comma 0, I would be at 0, wouldn't I? Okay, at pi over 2, I'm going to be at my highest amount. So at pi over 2, in this case, I'm going to be at 4. So let's use tick marks of 1 here. I've got fit on here, 1, 2, 3. Okay, so at pi over 2, I'm going to be at my highest amount here. I'm going to be all the way up here at 4. Okay, at pi, I'm back to the ordered pair negative 1, 0, aren't I? So the sine of pi is 0. At 3/2 pi, I'm at 0, negative 1, so the sine is negative 1, but I have an amplitude of 4, so that means it's going to go down here to negative 4, doesn't it? And then at 2 pi, I'm back to the ordered pair 1 comma 0, so I would be back to 0. So this will give me one period of the function to the right. This is the period that would go from 0 to 2 pi. I've got to do the period behind that. Well, I can go around my unit circle the other way to do that. So if I'm at negative pi over 2, I'm going to be down here at negative 1, which will wind up being negative 4 when I do the amplitude of it. Okay, at negative pi, I'm back to 0. At negative 3/2 pi, so going clear around this way, I would be at the ordered pair 0, 1. So that's going to take me to my highest amount, which is 4. And at 1, 2, 3, 4. Yeah, I got that. Okay, and then at all the way around here, I would be back to 0, like so. So I'd have the other period going like this, wouldn't I? Okay, so that's 2 full periods of that graph. Now, another thing you could do if you wanted to is you could graph this on your graphing calculator. To do that, you would just type this in your y1 right here. So we would put in 4 sine x. Okay, I could set my window to go from negative 2 pi to 2 pi. And let's go in increments of 1/2 pi. Because that'll tell us kind of where those zeros and those high and low spots were. I don't need all this height on here. It's going to go from negative 4 to 4, so I'll make it go from like negative 6 to 6. So I have a little room for tracing, but that's all I need. Okay, I am going to check my mode. Double check that I'm in radians. Okay, I am because I set my window up to be in radians, didn't I? And now I'm going to push graph. So this graph on my calculator confirms exactly what I have over here, doesn't it? And you can see from the half pi increments, the zeros are at negative 2 pi, negative pi, 0, pi, and 2 pi, and that's exactly where we had our zeros, isn't it? Okay, very good. All right, let's look at number 2. It says we're going to graph y equals 2 times the cosine of x. Y equals 2 times the cosine of x on the same interval from negative 2 pi to 2 pi. All right, now, if you wanted to get really brave, oh, wait a minute, I've got to go back to number 1 here. We forgot to write how the graph is related to this graph right here. Okay, we could say that the graph of y equals sine x, sine x, has been, okay, now we're going to tell, how many times louder. Well, we could do it this way. Let's put the 4 on here. Let's say the graph of y equals 4 sine x. I'm going to change this to is, okay, is 4 times as loud as the graph of y equals sine x, right? Because that 4 in there is the amplitude, which makes it louder, okay? Another way of saying this is to say the graph of y equals sine x has been vertically stretched by a factor of 4. We made it 4 times as loud. The parent graph would only go up to 1 and down to negative 1 and so on. We're going to make this 4 times as loud. Okay, forgot to do that. All right, let's work on 2 cosine x. 2 cosine x. So if we were to take that and look at y equals 2 cosine x over 1, the a value again would be 1 and the b value again would be 2. So the rule would be s, x comma y, equals 1x comma 2y. This time it's going to be part of a cosine function though. So if we wanted to look at that, we could just look at the graph of it here. I'll change this to a 2 and I'll change this to a cosine. Okay. It's going to go as high as 2 and as low as negative 2 on the amplitude. All right, so I'm going to change my window just a little bit here. I don't need all that high on there. I'm going to go, I'll have to go negative 4 to 4. But I still want to keep the rest of this on negative 2 pi to 2 pi, don't I? Okay, let's graph it and see what it looks like. Remember, the cosine function is going to peak out right here, isn't it? Okay, so if I say that this is 2 and this is negative 2, we're going to get a peak right here at 2, aren't we? Okay, at half pi, we are at 0. At 1 pi, we would be at negative 2. At 3/2 pi, we'd be back to 0. And at 2 pi, we'd be back to our height of 2, wouldn't we? So this would give me one period of the function to the right. Going to the left, I'm at 0 at half pi. I'm at negative 1, which actually is negative 2, the lowest point at pi. I'm at 0 at negative 3/2 pi, and at 2 pi, negative 2 pi, I'm back to my highest amount, which is 2. So we would bring this down and bring it around like so. Oops, I kind of missed that. Okay, that's 2 full periods of the cosine graph, isn't it? All right, the period of this graph is 2 pi times the absolute value of a, which in our case is 2 pi times the absolute value of 1, giving us 2 pi for the period. The amplitude is the absolute value of b, so that's the absolute value of 2, which is 2, which means it's going to go up to 2 and down as low as negative 2, doesn't it? The frequency is 1 over the period, so 1 over 2 pi, meaning it cycles 1 time in a linear distance along the x-axis of 2 pi. How is the graph related to the graph of y equals cosine x? Okay, we could say the graph of y equals cosine x has been vertically, if I could spell, stretched by a factor of 2, because remember the parent graph would go up to 1 and down to -1. This one's going up to 2 and down to -2. Okay, making the graph 2 times as loud as y equals cosine x. It's going to be twice as loud, if that makes sense. Twice as loud because we're amplifying it, aren't we? Okay? Amplifying it. Okay. Well, let's try number 3. Now number 3 looks different. If you match this up to y equals b times the sine of x over a, this will wind up being y equals 1/4 sine. Multiplying by 2 is like dividing by what? 1/2, isn't it? So a is going to be 1/2 and b is going to be 1/4, isn't it? Okay? So we want to know what's the period of this graph. The period of this graph is 2 pi times the absolute value of a, which would be 2 pi times the absolute value of 1/2. That's going to give us 1/2 times 2, or just pi. So it's going to be a shorter period. The amplitude is the absolute value of b. That's the absolute value of 1/4, which would just be 1/4. So this graph's only going to get as tall as 1/4 and as low as -1/4. So it's going to be not a very tall graph, just a little itty-bitty graph, not very tall. Okay? The frequency is 1 over the period, so it's 1 over pi. It's going to cycle 1 time every pi. 1 time every pi. So how is it related to the parent graph? All right, well, let's tell what these things do to the parent graph. Okay? We're going to say the graph of y equals sine x has been horizontally. Okay, now that's our a value that's working on horizontally, right? So horizontally stretched by a factor of 1/2, meaning it's actually going to be compressed. Okay? Actually, maybe we should put that. Let's put it as compressed. Okay? And vertically, let's say the same thing here. Compressed by a factor of 1/4. So this means it's going to cycle more quickly but not be very tall, right? So it's going to cycle more quickly and not be very tall, so it's going to be a higher, softer pitch. So the sound that it would make would be really high but soft. High but soft. So maybe something like a mom singing a lullaby to a kid because you didn't want to sing it high but pretty soft. Okay, let's try number 4. All right, we're going to say that y is equal to 6 times the cosine of x over 3. Multiplying by 1/3 is like dividing by 3. So a is 3 and b is 6, right? All right, if that's the case, the period is 2 pi times the absolute value of a. Whoops. So that's going to be 2 pi times the absolute value of 3, which is going to make this be 6 pi. So it's going to be a really long period, okay? The amplitude is the absolute value of b, which is the absolute value of 6, meaning it would be 6, which means it's going to go up tall and it's going to go down low. It's going to go as high as 6 and as low as -6, which means it's 6 times louder. The frequency is 1 over the period, so 1 over 6 pi. It cycles once every 6 pi. So from this lowest point over to this lowest point, the linear distance along here would be 6 pi. How is this graph related to the graph of y equals cosine x? Well, the graph of y equals cosine x has been, okay, let's talk about this first, horizontally stretched by a factor of 6, and then vertically, wait a minute, by a factor of how much? A factor of 3, that's the horizontal. And then vertically stretched by a factor of 6. Okay? So in this case, if we wanted to talk about what's really going on with this thing, this one's going to be 6 times as loud, right? 6 times as loud, and pitch is lower. So this is the guy that you come up next to at the stop sign and you hear the boom, 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 boom in the car next to you, and it's rattling the windows in your car. That's the increased amplitude and increased period. So it's really low, boom, 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 bass. Okay? All right, let's see what number 5 says. Number 5 says the graph below shows y equals the cosine of x and an image of y equals cosine x under a scale change. We want to find the equation for the image. To find the equation for the image, that's my pen here. To find the equation for the image, we need to find the value of a and the value of b. So first we have to figure out which one's the parent function. All right, the parent function. So let me take this blue, and I'll go over the parent function for you here. The parent function goes up to 1, and, oh, I didn't do blue, I did red. Up to 1 and down to -1, so this one is the parent function. Okay? If we can figure that out, that we're talking about this one being the parent function. Because the parent function would have an amplitude of 1, the b value would be 1, and the period would be 2 pi. Okay, so we're going to go to this other one here. I'll do yellow. And let's first of all figure out the amplitude. It goes from a high of 3 to a low of -3, doesn't it? So from -3 to 3, we have 6 units. I'm going to take half of that. So the amplitude is going to be 3. Okay? The amplitude is going to be 3, so I'm going to put 3 from a b value right here. Okay, the period, if I go max to max, then the period of this thing is how much? 6 pi, isn't it? The period is 6 pi. If you went from the lowest point to the lowest point, you'd go from -3 pi over to +3 pi, but we've got a total of 6 pi right there. Okay, so what we're going to do is we're going to use that fact that the period is 6 pi, and we're going to work backwards. 6 pi is equal to the formula 2 pi times the absolute value of a. Period equals period. Okay? Which means a has to then equal how much? 3 or -3. We'll just call it 3. That'll make it easier. Okay? Alright, now we're going to slip this into the formula. Y is equal to, now from this graph you might be able to tell that it is a cosine graph because it's peeking out right here. So we're going to slip it into there. We're going to have our b times the cosine of x over a function. So y is equal to 3 cosine x over 3. There aren't any complex fractions, so you can just leave the problem just like that. And so that would be our equation. You could graph it to verify it if you want to. Okay, and then last but not least, we have suppose a tuning fork vibrates with a frequency of 440 cycles per second. So they're giving us the frequency at 440 cycles per second. If the vibration displaces air molecules by a maximum of 0.2 millimeters, give a possible equation for the sound wave that is produced. They're going to tell us that it is a possible equation because it's a sound wave and we could use sine or we could use cosine. So that will kind of be our a decision to make here in a little bit when we figure out everything we need to do. Okay? All right, we know that we have a frequency of 440 cycles per second. Okay, and frequency happens to equal 1 over the period. Okay, 1 over the period, which is the formula 1 over 2 pi times the absolute value of A. So that's the formula that we would be using for that. Okay, and frequency happens to equal frequency, so 1 over 2 pi times the absolute value of A equals frequency, which is 440, and we could say over 1 if you wanted to. And then you could cross multiply this. So you'd have 880 pi times the absolute value of A is equal to 1. So the absolute value of A is equal to 1 over 880 pi. 1 over 880 pi. So that's what the value of A is in our problem. The B value, it says we're going to displace the air molecules by 0.2. So that tells you they're getting moved up 0.2, down 0.2, and so on. So we're going to use 0.2 for that. All right, so we're going to say y divided by b is equal to, and our choice is sine or cosine. So when it says you're doing a sound wave, that means you can do sine or cosine. I'll just say sine. Okay, and then we would have x divided by 1 over 880 pi. Okay, now we have to clean that up. X divided by 1 over 880 pi would be like x times 880 pi over 1. So we're going to wind up with y equals 0.2 times the sine of 880 pi x. 880 pi x. So you see how this is, the frequency is 440 and here it's 880 pi. It's like taking that 440 times 2 pi, isn't it? Times 2 pi. Okay. That's really all there is for this lesson. If you need to go back and review it again and watch the video again so you can understand the parts, that's fine. If you didn't get the note card written down, I hope you'll go back and pause it and get the note card written down. It'll be really handy for you to have. I would go ahead and read about this in the book. We'll be doing a lot of problems out of the book when we get together. If you have any questions, please come and see me.